Somebody remind me if I forget to do that in these classes, just because this gives you the chance to review the stuff afterwards. Okay. Hopefully it is actually recording. Yes, it is. There we go. Okay, so that's the basis behind what we call gradient descent. Why is this the gradient? Well, I'll come to that in a second. So here we go. So this is sort of a recap of this. Here we have this cost function. This thing is the gradient, dj dw. It's the gradient with respect to w. Right? Now and again, this is an expected value operator. So y star is a random variable. Y, which is equal to w transpose x, is a random variable because x is a random variable. W is an interesting thing. I mean, technically, yes, it's a random variable because it's going to depend over time on these values of y and x. But we usually think of it at any instant in time as being not random, right? So that in the sense that here's my w now, I don't know what the next value of x is that I'm going to get. So w is a fixed value, and I'm going to get a value of x that is now going to come in as a random value. From that random value, I'm going to change my fixed value of w to something else. But if you could say, if you look at w over time, yes, it's changing. It itself is a stochastic process. And I don't want to deal with that right now, but at some point we may talk more about that. So you have a cost function here. We have the gradient of the cost function, which I wrote before, and then gradient descent. Now, what is gradient descent actually, and then convergence? So what happens here, if you look at the gradient of w, I get this dy dw. Again, y equals w transpose x, so dy dw gives you this x transpose. And now dj dw equals that. And the key to all of this, so let me go back a second. What happened here is I took our version of the perceptron algorithm and I showed that it was descending this gradient. Now what I want to do is go the other way. If someone hands you the gradient, how do you create the algorithm from it, right? So I start out saying, we've got this algorithm. For this cost function, it descends the gradient because this turns out to be true. Now I want to go the other way, and I want to say, if someone hands you a cost function, they handed you this particular cost function, can I design an algorithm that I know will always descend that gradient, right? So I take that cost function, I figure out what the gradient is, right? And that gradient depends on my network structure. But I don't have an algorithm yet. I just plugged the network structure in, dy dw. Now I say, okay, this is the gradient itself, written with y taken out of with dy dw out of the equation. So this is the actual gradient, right? So now what do? I'm going to say dw dt. So back up a second. Sorry. What I want to do here is I want dj dt to be less than or equal to 0 at all points. Right? And I know that dj dt equals dj dw times dw dt, right? That's this thing. So I want this thing, which is dj dt, to be less than 0, right? So what's a way? How can I make this happen? Well, a very simple way to know that something, if I know something x, if I know a, and I want to multiply times b to make sure it's less than 0, a good thing to do is to set b equals negative a, right? And then I'm just going to get negative a squared, and I can be pretty sure that's less than 0. Right? So that's the basis. That's the concept behind gradient descent algorithms, which is all you have to do is my algorithm, dw dt is the algorithm, okay? I'm going to set dw dt equal to negative dj dw, right? And that then makes it such that when I multiply these to get dj dt equals dw dt times dj dw, actually the other way around, I'm guaranteed that that thing is going to be less than or equal to 0, and that's all I've done here. So now I take my dw dt, I set it equal to this. Remember, this thing here looks like the algorithm, right? That looks like the perceptron learning rule. There's a gamma in there. But if I take that and I put dw/dt, look what happens. The same thing that happened before. This is greater than 0. Sorry, greater than or equal to 0. This thing is strictly greater than 0. And I have that negative sign. Oh, where did that negative sign come from? It came all the way back from here, from the cost function, from the fact that it was y star minus y squared. Okay. What would have happened if you did y minus y star squared? It still works. It's just the signs, it's a little bit, the signs come from somewhere else. But so the point is, this trick is the concept of gradient descent. And what you're basically doing is you're saying, okay, let's look at what this means in terms of, so suppose this is the J of W space, okay? And so this is the space of W, we're looking down on it, and it's kind of like a series, it's a topo map, right? Coming up toward you like a bowl coming out of the, coming up out of your screen. So what I'm gonna say is these are my gradient directions, and I'm just, that are pointing downward. Well, actually, let me do this correctly, I'm sorry. The gradients actually point up, right? So if I have a topological map like this, the gradient directions for J are always pointing up. They're pointing up the sides of the bowl. If I looked at this thing in side view, looks like that. These are my gradients, right? So dj, dw, right? They're just the tangents. Okay, sort of a two-dimensional tangent. So those tangent lines are always pointing sort of up. And so what I'm going to do is I'm just going to set dw dt to be the negative of that. It's just, I'm going to point down. If I want to do gradient ascent, then of course I don't put the negative sign in there. No? Questions? Watch my time here. Okay, good. So so that's the concept behind gradient descent. This is super easy, and just knowing that, you can do a huge amount of very powerful things, right? This is used for optimization in lots of different places. It's an iterative optimization technology, and there's a lot of different ways and a lot of variations on this, and I'll come to some of those later. But before I do that, let's talk about this again in the more general case. So this is what I was just talking about. If you set the weights to descend the cost gradient. So this, again, remember dw dt, this is your algorithm, and this is your cost function. So you set the algorithm is to go in whatever direction causes your cost function to decrease, right? It seems pretty basic, right? If you want to get to the bottom of something, walk downhill, right? Sooner or later, you'll get to the bottom. So if you set the weights to descend the cost gradient, if you do that, then you will always have dj dt is less than 0, technically less than or equal to 0, because at some point you do hit the bottom. But for any finite gamma, so if your delta w is equal to some finite gamma times y star minus y x, right, where gamma is strictly greater than 0, greater than epsilon, greater than 0, then for that, you'll never actually get to 0, right? You'll always bounce around in the bottom. You'll be sort of bouncing around back and forth down here. So, but the point is, it will bounce around, but the expected value of this will end up being 0, being minimized. The expected value of J will be minimal. And in fact, if you look at the expected value of dj dt, will be less than or equal to 0, because again, once you get down there, the expected value of this will be 0. So it will, even though it's bouncing around on time points, on average, it's bouncing around the same point. So the expected value will be there. And we can sometimes write this in a simpler form, dj, or just a different notation. We use this gradient operator, del j. For people who haven't seen it, we pronounce it del. In LaTeX, it's the nabla operator for some reason, and times w dot is less than 0. So that's the that's the simplest way to write it. And the definition of that is that del j is equal to it's again, j is a scalar, right? It's a cost function, but it's del j is a vector, because this can be written as dj dx1, dj dx2 dot dot dot. So this thing here is a vector. And like I said, del, so if I have a cost function here, the gradient is a series of vectors in the space, or this should be technically, it should be dw1, dw2. So there's a series of vectors in the w space. And so this here is that's a dot product, because w dot, of course, is dw1 dt, dw2 dt, and so on. So these things are both, so this is a vector, that's a vector, and we're going to take the dot product of those two vectors to get a scalar, which we're going to say is less than 0 or less than or equal to 0. Yeah. So that's a terminology. So, and you'll see it's very common to write these things this way, and this is sort of the standard multivariate calculus of this stuff. Now, when you actually look at these things, there is a very important result which we sort of take for granted, but I want to point this out because, again, you know, I've been sort of tossing these things around, throwing in expectation operators, converting these to differentials. You know, I've said at various points along the way, you kind of have to throw in expectation operators at various points. Okay, what's actually happening here? There's a couple of people have looked at this. The classic paper on this was from Leonard Leung in 1977. And when you are implementing neural network algorithms, there are always difference equations. You know, there's time is discrete. Every time you go through your learning loop, you're going through the loop. There's a counter. T is 1, T is 2, T is 3. It's discrete. And of course, differential equations don't operate like that. They're in continuous time. Now anytime we simulate a differential equation, yes, we do it in discrete time, but there's a variety of ways of integrating these things: Euler methods, Runge-Kutta approximations, various other things that are used to try to figure out how we how we can implement or integrate differential equations. But the important thing is that they're not the same, and they do behave very differently. So the kind of thing that we're looking at usually for a learning algorithm is a difference equation. Right, it's saying delta W at each time point, and there's always some function here, right? There's a function of, usually these are error driven, so I'm going to say that here's the error, y star minus y. Usually there's something of the weights, and ET might be all of the inputs, so that's the error and the x, so it's all coming in there, right? And so what's happening here is that you have some function of your inputs E, and then you have and this is not, this is your thing there, but this is multivariate because you need to know what X is. But Q is basically whatever your learning algorithm is. So I'm just going to use Q in this case as the general representation of a learning algorithm. And so all of these learning algorithms are going to have the thing you're trying to learn and the sample data that's coming in from the outside world. Okay? And so, and there's going to be some fixed rate gamma that's going to say we're going to do a little bit at a time. And the importance of doing a little bit at a time, if I can go back to the gradient descent stuff, you know, again, imagine that I'm trying to descend here, right? So here's my minimum of J. This is J of W, and I start at some W0 point here, and I just want to descend that. That's fine. And so what I'm going to do is I'm going to move W a little bit in the direction of the descent. But suppose that learning rate is really big. Now I go, whoa, I'm over here. Too big. Okay, so this goes way up there. Okay, fine. So this is going to send me back in the other direction. But then it goes, wait, I start here, I go, whoa, I'm way over here. And now this thing's just going to explode. Right, so you're going to watch the weights explode up. Right? And you'll see these explosions when you actually simulate this thing. You'll see the weights just sort of start to get bigger and bigger and bigger. And how far they explode actually depends on a lot of things that you don't have control over. So again, if we were to, there's different kinds of functions. So if I have a cost function that is very shallow like this, right? These gradient values aren't very big. So now if I take that W and I move along this by a small amount, gamma times the gradient, whatever it is, delta J, if I move a little bit by that, this gradient is small, so even if gamma is too big, well, I don't know what that was. There's too much stuff going on here. So if gamma is too big, it's not quite so bad. I may still go here and I'm getting a little bit closer, and I may still go there and I'll be a little bit closer, right? Whereas if I had a steeper cost function, now this gradient is bigger. So if I multiply those things, I might have gone too far and gone past and oscillate. And even then you can go a little bit past and you can come back because it'll still bounce its way in, right? And you can think of it as bouncing like this, right? You can think of it bouncing like, but if I bounce too far, I'm going to go there, 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 and I'm going to escape. Right? So so again, the size of that of the learning rate matters, and the reason, and it's not, there are ways to calculate the optimal learning rate. I mean, wouldn't you like it if you knew the gradient, you know your cost function? Why can't I figure out, okay, just go there in one step, right? And that's the Newton method, where you actually do that. You actually figure out, okay, how far do we go in that direction? It's not as easy as it sounds. In one dimension, Newton methods work fine. The way the Newton methods basically work is that you say, okay, I have again, in one dimension, if I'm here, I figure out the direction I want to go. Okay, so this is the direction of the gradient, so one-dimensional gradient. And I'm going to move in that direction. I just figure out how far do I have to go to get to the minimum. And you can just figure that out, right? Just by sort of minimizing over this line. But now let's do that in 2 dimensions. Okay, so in 2 dimensions, if I have a circular thing, and I apologize for drawing one thing over another, but there it is. If I have a circular thing like that, and now I say, okay, here, I'm here, that's my direction. Newton method still works. I can, okay, there we go. That's where I want to be, and I'm going to stop there, and in one step I get there, right? But now suppose that it's not quite circular. Suppose that it is a little bit more oblique like this. Okay, that's not so bad either, right? So now I'm going to start up here, and I'm going to ask which way does the gradient point? Well, the gradient here points this way, right? So so gradient descent, what I'd do, I'd go there, I'd go here, and I'll sort of circle my way in. What a Newton method would do is it would say, okay, go this far until you hit the absolute minimum along that line, right? And now what will happen is you'll hit the minimum in a line that's perpendicular, and now go this far, and now in 2 steps you'll get there. So these Newton methods tend to converge in a number of steps that is proportional to the dimensionality, right? Whereas the gradient descent methods tend to make the same step size on each one, and it takes a much longer time to get there. And the amount of time depends on how steep is the gradient, how far away from the optimal do you start, and what's your learning rate. But just be aware that this use of these sort of constant learning rate gamma is only one way in which you can traverse a gradient system. Right? Because often you know a lot about these things. Often, like again, in many of these cases, you picked J, so it may not be that hard to find the minima of this thing as you go, right? Sometimes you can just minimize it. I mean, we have a variety of different ways of minimizing functions. And that's all you're trying to do. You're trying to find the minimum of function. Gradient descent is one of the easiest ways to implement, but is in some ways one of the stupidest. Because again, if I hand you the equation for an ellipse, you know where its center is. You don't have to do gradient descent to find it. But suppose you are trying to do gradient descent. So suppose you have an algorithm like this, and you are trying to do this with these gammas. Now, if gamma was the same at all points in time, you're going to get to the bottom and you're going to wiggle back and forth, right? And that's okay, you're going to wiggle. But what people tend to say is, well, how about as I get closer and closer to the bottom of this thing, I slow down. Now, there's going to be a little bit of slowing down anyway, because if you look at these things, again, remember the speed of this depends on the steepness of the gradients. So the gradients are big here, and they're going to get smaller and smaller and smaller anyway. So you are going to slow down as you get there. But sometimes you want your learning rate to slow down too, and that'll kind of freeze it in there. People call this an annealing scheme, because what happens in annealing is as in an attempt to make a perfect ice cube or a perfect solid of some kind, you cool it, but you cool it with a schedule. You don't just cool at a constant rate, but you're going to cool slowly, and you might cool it more slowly as you get down there. And so that behaves a little bit like a temperature, right? Things that wiggle around behave like temperatures. So for the people who work in thermodynamics, the learning rate is sort of equivalent to the temperature, right? And it says, how do things bounce around? in the real world, it's exactly like that. I mean, if you take a bunch of particles moving in a fluid, and maybe they're magnetic particles and they're sort of attracted to something and they're moving by Brownian motion, you can cool this and they'll get slower and slower and slower as they get closer and closer to whatever their minimum energy state is. I believe the book does go into particle systems later. So anyway, but imagine a stochastic difference equation driven by some kind of an error signal. Now, what we have here is again, as I was saying, this is, come on, oops, if I talk too much, my pencil shuts off. Let's take care of that. So now we have here a difference equation, and we would like to say under what circumstances can that thing be approximated by this differential equation? And you think, my God, differential equations are more annoying than difference equations, but it's almost always easier to solve differential equations than difference equations, almost always. So it's much better to do this in the differential equation domain if you can. And one of the things that's important about that is if you look at this E is a measurement. That's a random variable. That thing is a random variable. Look at this differential equation. I've taken the expectation operator. There's no random variables left. This is an ordinary differential equation. This is a stochastic difference equation. So under what circumstances are stochastic difference equations approximated by ordinary differential equations, right? And again, so what's happening when you do gradient descent? If I knew the gradient at each point, I can just descend that gradient and get there. This is just an ordinary differential equation. There's nothing stochastic about this, right? But what's happening is in the difference version of this thing, I'm just seeing samples come in one at a time. I don't remember this. I can prove that this solves the case for this kind of cost function. But in the real world, when you actually are handed a problem, you don't know the cost function yet, right? I say, I think there's a Y star out there. I don't know what it is. I'm just being given examples, right? So when you're learning from examples, you don't have the whole cost function. You just have these particular samples. So you are going to operate in this difference equation world. And that's why it's stochastic. You don't know what example you're going to get next. So you might get this and you might bounce around and you might bounce around a little bit. And the question is, if you're trying to prove that the difference equation converges and you have a differential equation that does converge, when does the fact that the differential equation converges, when is that enough to be sure that your difference equation is going to converge? Does this kind of make sense? Stop me if this is getting confusing to people. And this is, the book talks about this as batch algorithms versus non-batch algorithms. And the reason there is if somebody hands you all your examples at once, then you use the batch versions of these things, which look a lot more like the differential equations. So there's a series. So Leung, back to Leung, came up with the set of rules that says when does the difference equation and the differential equation have anything to do with each other. So one thing you need is that the data coming in have to be independent in some sense, so that you have to be getting samples that don't have to do with each other. I get a sample of X and Y. Okay, the next sample of X and Y is another randomly drawn sample. Why is that important? Well, suppose I were a mean person and I knew you'd started at some point here. I could draw a particular sample, because remember, there's on average the gradient points this way, but for any single one, you might get something in a different direction, right? Remember, I said sometimes you're going to get things that are going to wiggle around. So on average, if I have a lot of them, I will eventually go, but I could always choose the bad ones, right? I could always choose the ones that sent you in the wrong direction. So the point is, if I chose those in sequence, I could push you off in the wrong direction. If I'm choosing them randomly, I'm not going to get 20 heads in a row, right? That's the equivalent of sort of saying, normally you flip a coin, every coin flip is independent, and so if I go right on the heads and I go left on the tails, on average I stay in the middle, right? But suppose that I just said I'm just going to give you 30 heads in a row. Why am I to do that? I don't know, just because I feel like it. They're no longer independent. So now you're just going to go to the right and you're just going to keep going, right? So the point is that you need to be independent samples. As long as each coin flip is independent of the last ones, this is okay. Now, there are situations where things will be dependent on each other, where you're doing a filtering task, right? You want to estimate where you are, you're going to use this a neural network to estimate your position based on a sequence of GPS measurements you're making. So that would be a situation. Of course, those things aren't independent. They're GPS measurements, but they are conditionally independent given where you are at the moment. And we'll get to that when we start looking at statistics in the next chapter. Okay. So, so one of these things, you need the samples to be independent. You need the samples themselves to be bounded. You don't want huge values of X, right? That could be really bad too, because again, it'll just overwhelm these gradients. The gradients will be too big. They could bounce you too far. If the value of X is, so remember, there's almost always in these algorithms a gamma times X term. So if X gets really, really big, then it's as if gamma got really big. So there's when you look at these algorithms, there's almost always a gamma term there. Let's look at the actual algorithms here. Let me go back. I made a mess of this, haven't I? If you go back to sort of a standard learning algorithm like this, note that gamma multiplies y and multiplies x. So the correct value of gamma, or safe values of gamma that keep you from blowing up, are going to be determined by the scale of y and x. If you're measuring things in volts versus things, if you're measuring something in volts and you're trying to converge on that, and then you just decide somebody hands you the measurement in millivolts instead, you'd better divide gamma by 1,000. Right? So again, be aware that the scale of these things is important. It's the same thing if you're doing temperature annealing in Fahrenheit versus centigrade. You're going to need to anneal it at rates that are determined by the scale that you're using. Okay, so the ET needs to be independent, needs to be bounded, depends smoothly on XT. Generally needs to be differentiable. So wherever your state, the point is that you don't want to have crazy chaotic random variables, right? So suppose that you have the following function. Suppose that you're trying to approximate the function y equals f of x, where f is the parity of the 24-bit representation of the number x, right? How many bits are 1. So that thing is going to bounce all over the place, right? So nothing is going to learn that. It's going to look as if the data are going to look very random to the algorithm, and it's highly unlikely that thing would converge. But even if it did converge, the differential equation and the difference equation might end up converging to different things, and that's really what you're that's what this is about, is trying to get the differential equation and the difference equation to converge to the same thing. So you need that. You need W. The weights have to remain bounded. Usually we just enforce that. We say if the weights are too big, don't let them get too big, right? If W is greater than 1, then set W equal 0.99, right? You sort of let it bound. You reflect it at the edges or something. So, and that, it turns out that's not strictly valid to do it that way, but it's good enough, and that's what most people do. Or you just watch. If the weights are starting to get unbounded, then you call a halt to the thing and you start it again with a smaller learning rate. You need Q itself to be differentiable. So you want the algorithm to be differentiable. You need the expected value of Q to remain bounded as t goes to infinity. These things can be time varying. I didn't write that into t, but if this is time varying, then this expectation needs to remain bounded. And the rate I've been talking about can't be either too fast or too slow. What happens if it's too slow? If it's too slow, I'm descending this, you can get a Zeno's paradox, right? You can get, okay, I'm going to go from here I am, and I'm going to go in that direction halfway, and then I'm going to go that direction halfway of what's left, and I'm going to go halfway. And you'll approach that, but you'll never get there. But now suppose I go a quarter of the way. I'm going to grind to a halt about here. So the point is, you need enough gamma, you need enough of a learning rate that you're going to get where you're going, but not so much that you overshoot and bounce back and forth. So there's actual real criteria for that. Here's the criteria. Gamma, you want to go to 0. Gamma going to 0 means that you eventually stop, right? Not just an expectation, you actually stop. And the point is this differential equation, remember, there's an ordinary differential equation. This is just a function. So this is an ordinary this function of W, right? So this is an ordinary differential equation. You want it to stop. It's not a stochastic differential equation. It doesn't bounce. You just want it to converge. What you don't want it to do is go into the center and do little circles forever, right? So you want gamma to go to 0, so this thing eventually converges to something. You want the sum of the gammas to equal infinity. That guarantees that you'll always get there, right? That you won't have a Zeno's paradox. You won't end up stopping early because you just, there's not enough, again, not enough gamma to get you there. This makes sure there's enough gamma, no matter how far. Eventually, gamma has the power to drive you in. On the other hand, there has to be some value of p, and I believe p has to be greater than 1, for which the sum of gamma to the p is less than infinity. And usually we'll take something like sum of p squared is less than infinity, but it doesn't have to be the squared term. A good example for this is, sum of gamma, not sum of p squared. It's the sum of gamma squared. Gamma squared is less than infinity. Typical one is, suppose I say gamma of t equals 1 over t, right? So we know then the sum of 1 over t is infinity. And we know the sum of 1 over t squared is less than infinity, right? And so that says that gamma is not too big either, right? That it's converging sufficiently fast. And then there's this other term here which says that gamma itself isn't bouncing around very much, right? So that gamma t and gamma of t minus 1 are close to each other in some sense. So gamma can't be itself a random variable, right? It has to be, in some sense of smoothness. It can bounce around a little bit, but it can't bounce around a lot. So if you think about it, these things all make sense. People typically take 1 over t. In fact, you often don't even do that. Typically what people will do is that you'll take gamma looks like 1 over t and then converges to some finite number, epsilon greater than 0. So that gamma in that case might look like some epsilon plus 1 over t. Right? So it converges to some asymptote. Why would you have it not go all the way to 0? Well, you do allow a little bit of bouncing around here. And that has to do with the fact that things can be time varying. I'm going to use a blank spot here. So suppose that I have something which is actually changing with time. I have y is equal to f of x and time. And maybe I'll even make it a little bit, I'm going to make it a little bit simpler than that. I'm going to say f time of x. So f is changing with time in some way. And it might just be the direction I'm going. Here I'm driving, I'm driving along a road. And at this time, I want to drive in this direction. And at that time, I'm driving in that direction. And now I'm driving in this direction, right? So if I were learning the direction that I'm driving, right, I'm just looking out the window and saying, what's the driver doing? And at this point, I converge. So I think this is my W's, and I converge to whatever they're going to be. So suppose W is converging to some asymptote. And now suppose at the same time that happened, that gamma is becoming very small. But now all of a sudden, I want W to change to a different direction. Well, gamma's down here already. So now W is just going to be very, very slow, if at all. And eventually, it's going to kind of not get where it needs to go. It will eventually get there because of the Leung terms. This term, gamma t equals infinity, guarantees you'll never really stop, but you'll be very, very slow. And now if it changes again at some other point, it'll be even slower. It will get there. You're guaranteed to get there, but it could be, a millennium before you do. So what happens is that people say, if we don't let gamma go all the way to 0, we keep it a little bit over 0, then you can kind of track things. You'll track that a little bit, and you'll track this one a little bit, right? And you'll track them. And this is exactly the way filters work, right? So if it's based on, we'll talk a little bit more about the relationship between them, but it depends on the assumption of what it is you think you're going to do. If you think that the correct answer is y star is equal to some form of w star x, right? And that this thing is fixed, it's a constant value, then you might as well have gamma go to 0, because there's exactly one value and that's it, right? But suppose that instead you think that y star of x comma t is equal to w star of t transpose times x. Now what's happening is that w is not fixed. This is time varying. And because w star is now time varying, you don't want gamma to go to 0. because W is going to keep changing with time. Now, Leung doesn't say anything at all about that. He's just asking, when do these things converge to the same answer? This is no longer convergence, this is tracking. There actually aren't good theorems about that. Like, under what circumstances does a differential equation track a difference equation? The reason there aren't good theorems about that is because it's very easy to come up with counterexamples. Chaotic dynamic systems, for instance, are very sensitive to initial conditions. So if I take a chaotic system, which has, say, positively Lyapunov X-men, so that things are diverging even for very close points, and I start with 2 points, they're even a little bit further from each other. One of them is going to go this way and one's going to go this way, right, along your isocline boundary. And so if this happened to be a chaotic system, now that means that if I have a discrete thing bouncing down like that, and I've got a continuous one that's approximating it, they're going to have some finite distance between them. Now, they may be getting closer to each other, but there's always going to be some finite distance between them. If they end up in a region of state space with chaotic behavior, they're just going to diverge from each other. Right? Now, if things are not time varying and you follow the Leung things, they won't diverge fast enough. It won't be a problem. And one of the reasons it won't be a problem is because Leung prevents chaotic systems. This EQ remain bounded, and it turns out that the combination of this, and this basically prevents chaotic systems as examples of this. But you may want to track a chaotic system, right? Or something that's near chaotic, or just has strong some kind of sensitivity to initial conditions. I mean, it's not unreasonable to do that. And so the point is that there will always be cases where things are a little bit wrong, right? So for any finite value of gamma, if gamma is greater than epsilon, which is greater than 0, and I have some boundary, let's suppose I'm driving, one of my favorite examples, you're driving on a road here, and you've got a cliff off this side of the road, okay? And you're driving your car, badly drawn car, but you know I got it. You're driving your car along that road, right? Now and you're driving it using a finite gamma. So I'm going to go here, I'm going to go there, 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 and oops, I'm off the edge. Okay, so now my car has fallen off the edge of this cliff. Okay, but my differential equation might have smoothly stayed on there, might have gotten very close to the edge, asymptoting, but not gotten there. So the point is that you can have very different behavior of these things. And you may need to study that. You may need to bound what these different behaviors are. And again, this corresponds to oversteering. That's what happens when people are drunk. So this is one of the reasons you don't drive drunk. It's also the reason that if you're building control algorithms for cars, you have to be very careful about it. Obviously, you try to smooth these things out. If it's too smooth, you won't make the curve and you'll go off this side or you'll go off that side. If it's not smooth enough, you'll bounce back and forth and you might bounce off the edge. So the point is that it's worth keeping track of these Leung conditions. Again, they show you convergence for a static system. For a dynamic system, we'll have to put bounds on these things. We'll talk a little bit more about that. So I'm going to stop there. It's 3:20, and as I said before, I will sort of hang around, just leaving Zoom on for about the next 40 minutes, a half hour. So I have to stop a little bit before 4. But if people have questions and want to talk to me about whatever, that sort of functions like office hours. There's no need to show up, but I'll be here. Sort of vaguely paying attention to the screen. Before I do that, are there any questions about the lecture today? Stunned silence. Okay, I'll take what I can get. So let me see if I can probably stop we'll stop the screen broadcasting here. Bring you all back. Okay, good. The other thing is, I don't think Monday is actually an official holiday. It's Columbus Day, and I wasn't planning on doing classes that day. So we'll, in honor of Columbus and many of both the good and bad things that he accomplished for the world, we won't have class on Monday. We will have class on Wednesday. and that also means that you have a little bit more time to submit your revised homework 1, right? So homework 1 should be pretty standard. People sent it in today. You can send me the revised one by next class, plus your initial stab at homework 2. Again, I'm happy to answer questions. So thanks, and I'll be here for a bit.
Do we get any kind of feedback on the first submission of the homework, or no?
No, not really. I'm just going to. I'll do it all at the same time. Again, the only difference is that it'll be sort of effort points, which is just I want to see people tried. I don't want if you know what I'm talking about. I just don't want people to sort of scribble something on a piece of paper and send it to me and say, look, I got it in. Okay. But I also am very willing to see that since we haven't had a lecture on it yet. You won't necessarily know what the right answers are. These things are going to get harder as the quarter wears on. The main thing is I want to make sure that people have read the chapter prior to the lecture, because as you see, I'm not exactly going through the chapter. I'm going through a lot of the concepts in it, but I'm trying to add to it.
Someone also asked in the chat if we have office hours next Monday.
I don't think so. But you guys can email me if you guys have questions. And speaking of office hours and things, I'm going to stop the recording.